parity breaking, and Wu. They said, look, we can do like this. I cannot write, that's for sure, a potential which is non-singular everywhere, right? Because there is a singularity. I mean, what is happening here at one point where I put it at 0, there is a singularity. I say, so why don't I do the following? Why don't I will work in spherical coordinates because of the spherical symmetry. So why don't I introduce, I'll pretend, a potential, but let me call it north. I'll define it in the northern hemisphere. I can do that. I'm not pretending that I can. This you will see at the moment. It will look like this: Gm over 4pr. I will 1 minus cosine theta over sine theta times unit vector. Fine. Notice that this is non-singular. See, if you try to extrapolate it, oh, by the way, let me check. Let me check that I get the right result. Delta has, you know, there are now, when you do the curl in spherical coordinates, there are many terms, but there is only one that deals with phi, and it looks like this. It's 1 over r sine theta, d over d theta, a phi sine theta. This is the formula. This is the only term that survives. Check it if you look at the handbook. There are many terms, but there is only one that acts on a phi, and a phi has to be with sine theta. So what do we get? We get the Gm over 4 pi r squared, because there is 4 pi r, there is 1 over r, 1 over sine theta. A phi times sine theta is 1 minus cosine theta times r. This is precisely, you agree, what I wrote before. Or there is r squared, so I get Gm 4 pi r squared times r. In other words, it is perfectly valid, but it is singular, okay? You could always find singular such functions. Okay, this, for example, if you go to theta equal pi, it's not well defined. But everywhere on the northern hemisphere, it's perfectly okay, because when theta is 0, apparent singularity actually is not there. Right, this is 0. How do you see that? 1 minus cosine theta goes as theta squared, this goes as theta. So it's small. So this is perfectly well defined in there. And they said, look, let's do the following. But it looks crazy. Right? I'll now do the same thing in the southern hemisphere. And it's going to look Gm over 4pr. Now it has to be 1 plus cosine theta divided by sine theta. I must have a minus sign in order that the derivative, notice the derivative will be the same. Okay, because it doesn't matter that I have a minus sign, I put 1 over plus cosine theta. This is for pi over 2 less than theta less than pi. This, of course, is singular at pi. At 0, not at pi. Okay, this is singular at pi, because this becomes 2 over 0, and this is singular at 0. Therefore, we have managed. We have managed to do apparent, well, we started to do something, okay? You can tell me, well, what happens at the equator? Do they meet? They should be the same. You would succeed, but then, of course, it's impossible. How can I succeed to do that if they are the same? Because I would violate. Well, maybe you can say, well, maybe because one is, you did something miraculous. Well, they are not 0. What do I get? An minus as at the equator. What is it? Equator, theta is pi over 2. So let's do, I will get Gn over 4 pi over r. Let me see, the first piece is, when theta is pi over 2, this is
I think it's over 2.
1. What? No, no, this is correct.
No difference. 2 times the difference.
Where was the factor? There was no factor of 2. No, it's okay. Gm over 4 pi r, 1. The first piece is 1 minus 1 plus 1. So Gm, sorry, it goes in direction 5, right? Is Gm over 2 pi r times 5. It's not 0, but it doesn't have to be 0. This is in spherical coordinates, you check immediately. It's a pure gauge. This is a lesson we keep repeating. When something is a pure gauge, it's 0.
Pure electromagnetic gauge.
Pure electromagnetic.
Do we have a singularity as the origin of this gauge?
This is an equator.
Do we circle the...
Right. There's no origin. Look at it. Gm over 2 pi 5.
Okay, it's the gradient of some function, so it's pure gauge.
This is pure, I just wrote it, it's a pure gauge, and the gauge is well defined. Well, there is a little more to it. Here comes the magic then. So I have AN, we have to have this. These were our crucial formulas. Then we got this, and this is equal to. Remember, however, when you have pure gauge, think of now having some fermion in your theory, and you and I want to formulate a theory with fermions, for example, electrons, or any charged particle, then we have a transformation which is e to the q. Remember how we wrote it? If I don't put q there, then I would have 1 over q here. I used to put 1 over q here. It doesn't matter. There was a relative. The gauge transformation has 1 over gauge coupling. Remember that relative. I'll put it here. He times 5. Okay, 5 with a charge q has to transform like this when A is a pure gauge. When you make a gauge transformation, I just made a gauge transformation like this, I have to get this. And now I have to demand, remember this should be single valued. I want my wave functions to be single valued. That means that e to the iq, e of 0, should be 1. Any case, put he 0, it's 1, you agree? But also, let me write separately, e to the iq, I of 2 pi, should also be 1. See what I have, it is interesting. Now I have the face here is actually 5, it's the space-time coordinate. This has to be 1. If you want to have a single value function, okay, this is Dirac's great result. He says, Dirac, I want to have a quantum mechanical theory of monopoles. So I want to deal with wave functions, and I want the wave functions to be single valued. And now I can compute here. Tell me, what is q, e of 2 pi? Is, yeah, let's together, q, gm. This has to be 1. Therefore, this must be 2 pi n. It's that simple. It took 15 minutes. I will have to think now in class. I've just proven charge quantization. Yes.
When we had magnetic monopole, we have now to change the kinetic term of F mu nu, the structure of F mu nu in the Lagrangian, or to stay the same, or we redefine F mu nu.
I can work like this. I managed to find for you the potential which is well defined everywhere.
You mean that we stay with the same structure of F mu nu with the vector A, and
Well, you have a current. F mu nu is nothing. F mu nu is just kinetic energy of the photon. It has nothing to do with this. There are no electric and magnetic fields. When you write to Lagrangian, which is F mu nu, forget it. This is just, there are no interactions. Then there is a interaction J times A mu.
what I mean is that we use that.
No, here it is, not here. Here there is nothing here. Here I have to worry about this.
Yeah, we use that we can write the Maxwell equations as the derivative of mu nu.
Well, these equations, it's here. You don't have to translate it into F mu nu. That won't help you.
Okay.
The equations for electromagnetic field transform into this. And there, of course, there is. And so on, okay, I don't have to write them, okay, I'm writing here only the piece which depends on the source. The things did change, and this is the change that you can write in the form of F mu nu, the delta V is now not zero. I've added a magnetic monopole. And of course, the potential is now very different from what I was used to, but I, for one, don't see anything wrong as long. Apparently you can say, well, you are describing two different functions. No, I'm saying it's one and the same functions, because where they meet, it's a pure gauge. Each of the functions is well defined in its parameter space, and when they meet, it's a pure gauge. Therefore, that's one and the same function, we would say. Both give me this. Gn delta function. I put a monopole at the origin.
How do we, in the Lagrangian we're going to write now, how do we introduce the magnetic charge? It will be just a current, like a magnetic current coupled like that. How do we?
How do you?
What do we want to add to the Lagrangian to obtain the magnetic charge?
You want me to now discuss the Lagrangian formulation of? It's not this piece, right? It's you want me to generalize it, but then it is this. You agree? It's not the. It's not here. It's here, the picture. How do I write the? This is J0A0. So how I'm gonna do this in Lagrange formulation? That gets a little messy. I don't want to talk about it. There is an approach, there are various approaches by Zwanziger. You can work, you would work with non-singular potentials. It's very hard. Or you can double it. There are people who have two potential formulation, which is non-singular. Of course, there is always something. You see what happens. There is a situation in which you have a pure gauge. It's there where the drama is happening. Okay. In the case of Dirac, there is something in which the picture is breaking down. Let's not worry about that. I won't talk about it. Working, it doesn't make sense that we now break our heads working with magnetic monopoles. Magnetic monopoles never found. Okay, so what we have to understand what would be the physical implications for charge quantization. It's a messy technical subject.
Is our potential continuous everywhere on the sphere?
Yes.
Shall we connect them? Like, because we take a difference at the equator, and it's not zero, it's some function.
No, it's zero. For us, For us, pure gauge is 0. We don't distinguish pure gauge
And
from...
we put the pure gauge on just the circle, not all the sphere.
Just where they meet.
Yes.
Of course, where they don't meet, they are perfectly well defined. They cannot be pure gauge where they don't meet, that's for sure. All I meant is that the equator, they are equal to each other, because the difference between them is a pure gauge, and pure gauge for me, there's no physical meaning. There is a physical meaning in this pure gauge. It's an unusual pure gauge. You see what we are proving, that if they are magnetic monopoles, the U1 group of electromagnetism becomes compact. You know, when we are getting eigenvalues are integers, okay, this happens only in compact groups. Whereas circle, the U1 we said had an arbitrary. We have modified the meaning of U1, this is true.
This also happens in Aharonov-Bohm effect, right?
Sorry?
In Aharonov-Bohm effect.
The Aharonov-Bohm effect is something that is related to the fact that in quantum mechanics the pure gauge potentials may play a physical role. We normally say that the potentials are irrelevant. In classical physics it is true, not in quantum physics. Here, for example, only by requiring, now this is where I go to the quantum physics, okay, the classical level that nothing like this ever appeared. There will be no constant because I would conclude nothing. Now I'm asking, I want to do it, and then of course you can tell me now, give me the quantum field theory of that, okay, that I don't want to do. That would be a course in itself. And it's not the way because liquid, and people stop worrying about the point monopole. I will go to something else, okay, as exciting as it is that there may be, you see what Iraq says, look, there may be a monopole somewhere there, and one is enough. I don't know whether it exists. If it were to exist, I would prove charge quantization. But then I don't know if monopoles exist. So I'll do something else much more interesting later on. I'll show you the theories that we like based on grand unification. Magnetic monopoles must exist. And they are not point-like, they are little balls full of Higgs field inside. We will see something much more interesting. So there we work with the ordinary field theory, and then within that field theory, you know, we find classical solutions. Then you can think how you quantize, how you do quantum mechanics on that solutions, okay? I've actually I've done here classically everything, I admit. Then I said, when I want to do a quantum mechanics, and I have to think how to, this will follow, independently of how I realize it. Whatever I do, this wave function has to be single value.
Professor, can you find the smallest value of Q from the
Yes.
equation? What is it?
It's there when n is equal to 1.
But n can also be 0, right?
N can be 0. Sure, if there is no monopole, n is 0.
No. Even if there is monopole, these equations are satisfied when
No.
n is equal to 0.
Yes, but if there is Q, no, that depends. If there is some charge, and there are charges, there is a charge, right? Down quark is the smallest charge we know. In the case, you have now applied to the charge, okay? Whatever you take here, you will get 10. So obviously the smallest number is for the smallest charge. And then larger charges would have larger n. N equals 0 are a particle without charge. Sure, there are neutral particles. That's neutrino.
But can you also say that Gn is also goes to 0, so we cannot say anything about the charge itself?
If there is no monopole, we cannot say anything. You're right. If Gn is 0, then there is no relation. That's good old
So
QED.
these equations are also true when monopoles do not exist.
Of course. Sure. Just take Gm equal to 0, and you are back to. Then you lose this. There is nothing to say there. There is nothing to write there. So all I'm saying, there is one monopole.
what makes us like really sure that our gauge theory will not change when we have magnetic monopoles?
What do you mean that the gauge theory? I don't know what you mean by that.
The U1 gauge theory, because
Well, it already changed.
how
It already changed. Charge has to be quantized. It didn't have to be quantized without monopoles. That's the first profound change. Now this is a prediction. No matter what happens, you can add whatever particles to the standard model. If there is one magnetic monopole, add those equal left or right. It doesn't matter.
but
The charges will be quantized.
Yeah,
That's,
but at this stage we're making the gauge transformation physical, right? Or no? If I think I misunderstood.
maybe not.
Yes, gauge transformation brings us this quantization information because our gauge should be compact and you need to have this. So like gauge field matters in this example.
Sure. How could it not matter? I have a monopole. I have a magnetic field. By the way, you may not appreciate this particular formula. No matter what formulation you do, you will find that the product of, there are different ones, like the original of Dirac, you always get the same position.
We can change the potential by any random gauge, but we will end up with the same condition. That if there is a charge, it should be quantized.
Yeah, this is of course independent. There is a physical result here. I got this physical result. Yeah, I got a physical result. This was a physical result. All I asked was, this is a single value. And I got this result. I suspect that this is true. Of course, you can ask me, show me another formulation which it happens. And yes, it happened. This is genuinely true.
So we just put a condition on our gauge transformation that has to be now periodic. So
No, it's not that. We just put a condition that this is well defined. We only asked that the potential describing the magnetic field is well defined everywhere. And at the same time, the wave functions of the electrons.
What does it mean to be compact for U1?
Compact is when the compact we call when the eigenvalues are like SU2 is compact.
Or
When the eigenvalues when
the parameters are like
right, it's not infinitely. This you are now in a circle, and you can go n times around the circle. That's a good way. The space of this transformation is compact. The circle is compact. Line is not.
we still have the gauge.
SO3 was SU2, was S2, remember that was compact. When we had group SO3, that corresponded, the vacuum manifold that we discussed that corresponded to S2, that also corresponded to here, for example, the charge is quantized and the manifold is compact.
for U1 is not a circle. No matter
U1 is arbitrary. No, U1 doesn't have to be a circle.
Circle is arbitrary. That doesn't
No, it doesn't have to be a circle. When you perform the transformation, nobody says that you have to do it in a circle. It can be a line. When I say that psi goes e to the I hypercharge times psi alpha phi, I never said that alpha goes from 0 to 2 pi. Because if it goes from 0 to 2 pi, then the single value noise will push me to have integer values only. No, it was arbitrary. That was the problem of U1. We often pretended that it's a circle because at the end charges are quantized. It is a circle in the standard model, okay. The group actually is compact. It turns out that the value, as if the standard model behaves as if there is a magnetic monopole. without asking for magnetic monopole. However, we said in the Sandor model, like in any kind of particles with arbitrary fractional charges, if there is one monopole, all the product of any charge times this will be true. It may be 0 when you have magnetic charge 0 or electric charge 0, otherwise it's an integer.
This condition is brought by the periodicity in space, right? If you had, like R3, in which we can put a condition, after 2 pi we came back to our same point or whatever, we couldn't say that. But here we have a circular gauge field on.
No, we ended up concluding that it's circular by asking this. We were not sure before. Only when we came here by asking single valuedly, it turned out to be
That's
circular.
single valuedness because of the our gauge.
Yes.
It's a phi coordinate, it's a
Yes.
physical coordinate.
Yes.
It's not some internal.
Okay.
So that's
Right. In the case of a monopole, I have a very particular gauge configuration in which this alpha is actually phi. But the trouble is about this that one monopole would suffice. And the joke was that that was the monopole that went to plates of Cabrera on 14th of February 1982. Cabrera at Stanford, he thought that he saw monopole somehow. He had some little thing, obviously it was not true. The joke was there is one monopole in the universe. And now it's, I don't know where it is now. Monopoles were never found. I'll give you some story about what we would expect about monopoles. What I want to do now, later, slowly, depending on your question, is the following. I've just shown if there is a monopole, then there is charge quantization. I want to show you if there is charge quantization, there is monopole. And this is much more interesting. That there are certain types of theories, and those theories have well-defined predictions, that among those predictions also say that there must be magnetic monopoles. That's much more exciting. And these magnetic monopoles actually are some physical objects that have their sizes and so on, not an imaginary thing that maybe is there in the universe. But okay, let's not move yet.
So the charge here and the magnetic monopole are the same, are for the same particle than the last question.
No.
No. So you consider like arbitrary magnetic.
No, this is not the same particle, but it's the same particle,
Is it
it's called ion. Okay. Right, no, this was, remember, this was some electric charge moving in the field of the monopole.
Okay.
There is a monopole out there, no, I'm thinking of ordinary particles like electron and downward, no.
Moving in.
I can think now what happens to the particle that have both electric and magnetic charge, okay, they're called ions, okay, but we can now enlarge the subject, okay. Here there was a particle of charge Q moving in the field of the feeling that field.
This wouldn't also quantize the magnetic charge.
Yeah, magnetic charge is quantized, obviously.
Okay, both of them are.
Obviously. But there is a duality. How could it be that one works? Look at these equations now. There is no difference. Look at these equations. Obviously, if one is quantized, the other will be quantized. What do you call a monopole? Now there is a tricky thing, okay? There is no electric or magnetic field, there is a complete duality. In one formulation, electric may become magnetic, okay? It's a matter of semantics now. The thing is, however, when Q is small, G is large, notice. So if you have weakly coupled theory with electric charge, it will be strongly coupled in magnetic charge, and that you don't know how to work, okay? True. And vice versa, if magnetic charge was small, electric would be large. You can imagine such states, okay, with huge electric charge. Then, you know, imagine they have particles with huge charge, then the coupling is actually, when I call it alpha, I'm always cheating, it's alpha times Q squared. can use the numbers of order 1, so we don't worry. Actually, they are typically other quarks we worry about, which are smaller than the electron charge, so it happens. There are some doubly charged particles, you may get a factor of 4. Now we know if there are particles with a charge 100, then such particles have strongly coupled interactions with a photon. A corresponding monopole would be weakly coupled.
This is true that there is a corresponding relation between the magnetic monopole and charge quantization within U1, if we consider only U1 to be the AN gauge theory. But I remember in the beginning that we show if we have a higher gauge theory which may contain within itself U1, it can be followed it follow without maybe speaking about magnetic monopole that charge is quantized, but that's different.
No, but I can actually talk, and I don't want to do that. I can extend the definition of monopole. There are sort of topological ways of talking about it. I don't want to do that. It's like charge. That only, I'm speaking in the conventional sense. It only makes sense to speak in U1. I'm speaking of normal electrons and normal monopoles, defined with respect, of course, to the U1 theory of electromagnetism. So this can be enlarged, and you will see why and how when I go into the sort of et Hooft monopole picture. These issues will appear. But even there, I will try to isolate U1. I want to find a monopole that has U1 properties. Okay. Turns out that you can get monopoles even when there is no U1. There is something very strange. But then these monopoles have a different meaning. You see, that's an extension of. You have to enlarge the usual meaning. I don't know if you paid attention because you must have. Maybe you go to some talks. People talk of extra dimensions. Right? You heard of that. Obviously, when they speak of extra dimensions, they mean something by that. They don't mean like these 3 dimensions. They cannot be. There are no 4 dimensions. There are 3 only. So now I have to sort of extend my definition what I mean by the dimension. Okay, this is very important. And we can do that. We can speak of extra dimensions, it will have a different meaning. Actually, 4th dimension just means that there are towers of states or some similar things, okay? But there is no... Okay, that's very important. So once I find that there is a magnetic monopole with some properties, I can then extend the definition, but it becomes formal. So let's stick to the real basics here. By the way, you can do the little exercise if you're not sure about this. You're saying, well, I don't know. No, I didn't erase it. You can say, I don't know whether you did the right job. You can say, look, if I'm right, you know that the flux, which is BDS, should be GM. Right? This flux has to be GM if I'm right. So what is BDS? That's Bn plus B south, which is the same. The contribution from north plus the contribution from south, let's say. What is the contribution from north? That's an integral of An dl around the equator, you agree? Okay? Right? That's what it is. You see, there is something going here and something. So notice now what is going to happen. If I go now, this one of course goes in the opposite direction, okay, the boundary. So this is minus A south dl. Agreed? If I'm looking south, then the boundary is in the opposite. I'm taking the same dl. Okay? if I'm looking for the nodes, this direction is opposite for the other guy. So this is actually the integral over En minus AS dl. But this is a pure gauge. And you will take the derivative with respect to phi. So it's gm over 2 pi. This is trivial. This is gm over 2 pi times the integral of d phi from 0 to 2 pi, which is 2 pi, which is gm. This is really a potential. Okay, you can calculate the flux by doing this. Okay, this is trivial, Gauss law. The surface is 4 pi r squared. Why don't I put r squared? It's better. But I got the right result. So once again, you can say that somehow this was fair, what I did. We studied at 4. I will now move to what is called the subject of topological defects. I wanna give you this at Hof monopole, but before I do that, I wanna give you a very simple example of what it means to find a classical solution, which sort of started the whole field. How in field theory you can, besides having a vacuum, we normally see what we did up to now. Always we found some vacuum and we quantize on that vacuum. In the beginning, vacuum was trivial. It was a zero value of whatever field we were talking about. So we never had to even think of what the vacuum physically meant. Then with the Higgs, it became something non-trivial. It carried some charge. We had to understand what it meant. Well, okay, we formulate our quantization rule on that thing. But we can imagine other objects which carry energy, which vacuum carries zero energy by definition. I normalize to zero energy. Well, vacuum may carry a little energy, right? Now you know that gravity, that now you are more educated. Gravity couples even to vacuum, right? Gravity will tell us what the vacuum energy is. There is a serious suspicion that it's non-zero. Did you talk about it? The acceleration of distant galaxies and cosmological constant? So this acceleration is most easily explained by the value of cosmological constant. That of course not conclusive yet. There could be other explanations of that. But it's the simplest, so it's like a kind of Occam's razors tell you that's probably what is going on. But it's a small number anyway, so I live in the, I don't know if I should erase or not. Are we ready? I'm not doing justice to this. This is so important, so beautiful. This is a field that people spent years working on. Precisely on the question that Mahmoud and then you were asking afterwards, how do you formulate now the field theory of this? How would you formulate the equivalence of QED with point monopoles? I mean, it turns out I sort of have emotional attachment to the field. I don't want to talk about it. My brother, late, whom I lost, worked a lot. He wrote some important papers, and the review, if you're interested in it, I can give you the review of my brother on the Lagrangian formulation of point monopoles. It's a physics report. I myself got interested in magnetic monopoles much more with the Hooft work. So I thought a lot about something that we'll talk about as we go on. So if you allow me, I'll now slowly introduce you. I won't manage today and some of tomorrow show you that if you believe in grand unification, there must be magnetic monopoles. But in order to do that, I want to discuss what is the simplest topological defect. It's called domain wall. And it goes like this. I'll take now, and this is actually, it's good that we have this now. I realize I'm kind of going back to where we started. I love that when whatever you work on takes you to the very beginning. That is what mostly enhances your understanding. I can tell you how you will know that you are doing really good research. You will know because when it's really good, it will take us to think about basics more and more. Remember this, because there is always a danger that your research takes you to endless manipulations further and further away of the questions you started with. And you can go on and like that, but you will find that with great pleasure and a deep sense of insight when, oh, it's the same thing that I wondered about when I was 10 or 15 or especially when you were beginning of graduate school. Okay, and we started with the spontaneous symmetry example, and I didn't even know what it meant. First, what was that example? A real scalar field with a symmetry phi goes to -5. I wanted to have a symmetry, and I wanted to break it spontaneous. And I took the potential, which I will take down lambda equal 1 or 2. To simplify calculations, I will write like this. The value of lambda is irrelevant. Anyway, it could have been 2. And it's similar to something. Higgs mass is about 120 GeV. Lambda must be order 1. Right? Gauge coupling is order 1. MW is 80 GeV. Higgs is there. So maybe it's even a reasonable thing. Okay? What we found out here, that the vacuum manifold was 2 points. Why? Because vacuum manifold by definition is the value when the potential is the minimum. Is at the minimum when it's 0. And that's 2 points, plus or minus V. Now, so we said, we live, you and I, in one of these points. It doesn't matter which we choose. That's called vacuum. Let's say phi 0, as I call it, is plus V. It could have been minus V. And I live there always. But the fact that there are 2 of them, it's sort of interesting. You can ask the question, well, the universe once upon a time was very hot. In fact, Mahmoud today a lot. Even that, why is it cold today? Hot is easier to understand in some sense. There is temperature and we can understand it. If it was very hot, could it be that actually there were other vacua? I mean, why is it that there is one vacuum? You can imagine that even there was a phase transition probably at some very high temperature. Water evaporates at high temperature. Imagine that at high temperature, you have a phase transition, a phi 0 goes to 0. Not impossible. Okay, why don't I show you that, by the way? Since you want to know, there is this beautiful work of Weinberg, in particular, I like a lot. 1974 classic paper, which it's not the original work that was started by Kirchnitz and Linde, Kirchnitz especially, but he shows you that the potential at high temperature is potential at 0 temperature plus when the temperature is much bigger than all the mass scales of the theory. It's not surprising that you get this. This is dimensional grounds. Temperature has a dimension mass in my strange units of H bar. And he computes A. He has a gauge contribution. He computes it for a general theory, okay, typical of Weinberg, because that's immediately generic calculation for any theory. And for example, if there is lambda, if the coefficients are positive, okay, I'm writing 1. You see what it means? At sufficiently high temperature, the symmetry is restored. what I'm saying, when t is much bigger than n, you agree that phi 0, phi, which is phi 0, will be 0. Okay? Once. Okay. When m square is positive, then the symmetry, the minimum is 0, of course. So then you can ask this question, and it is a question, then most likely when I started with this hot universe, it would be natural that there are domains. The whole universe cannot communicate to each other. You know that the universe is very big, you know that. But you must know that it's not only that it's today is big. When it was smaller, it was actually much bigger. Now what do I mean by that? This strange remark is actually true. When universe, how do I define the universe today? What is the size of the universe? Is what I see. I don't know how big the universe is, but it's at least as big as what I see. Okay? And that of course changed with time. People would see their village and they thought when people sailed and went further away, and every time they expanded well, they would see the stars and so on. Anyway, I'm sorry. And so slowly, you know how big this is, right? It's about 10 to the 30 centimeters. Am I right? 10 to the 28, I think.
28, yeah.
More is like 28.
You
Okay.
said 28 the first time.
Yeah, I want to round numbers. Who cares, you know? A little bigger. By the way, now these are precision high. Cosmology is becoming a serious science every day as we speak. It's become. So I shouldn't be so cavalier. But 10 to the 28, 10 to the 30. It makes all the difference. We are measuring the age of the universe with precision today. You studied this in the cosmology class? This is the inflation. You said nothing about inflation. Didn't hear not a word. But did someone told you about the horizon problem? So what's the horizon problem?
It looks like we have spots in the universe that are very
Right.
connected to each other, and they're
Right.
very
How do I?
communicate.
Why? How do I know that? Let's see now. This is a test always, you know, of learning, as you know. You learn and it's so clear. Then you have to tell it to someone. I'm always amazed how this level go. You know, first I tell to someone. That's sort of easy. Then I tell to a more educated collaborator. That gets a little tougher. Then comes a moment when you have to teach. That's yet another level. You know, everything that you thought was clear becomes murky again. Okay. So why? So today there is no horizon problem. The universe is horizon. The thing is that horizon goes as time, and time in gravity is what? As temperature. They're related to each other, time and temperature. That's called Big Bang. This is the essence of your cosmology class. I want you now in 2 minutes to summarize your knowledge of cosmology for me. How does it, time goes with temperature? It was hotter in the past. 1 over time, 1 over t?
Depends on the count. But
No, it's not 1 over t. The horizon, no. Time, no. You see, gravity must enter there. This you studied in Einstein's theory of gravity. When you formulate your Big Bang, use Einstein equations imagine you did what? You studied, right, Big Bang. Right? So you imagine that the universe is very symmetric, isotropic. At large scale, it seems to be so, strangely enough. Okay, it's very anisotropic now when I look at you and you look at me. And no, Planck scale must enter. Just remember, it will not be that without. The whole thing is happening because there is gravity. That it goes something. I don't care now about coefficients. There is always a coefficient that is over 1. Dimensionally, it's temperature squared. The effect is dramatic. The universe was really hot when it was young.
Is it coming from Friedman equation also?
Yeah, sure. Well, Friedman, it has to do with the fact that when you write Einstein equations, you need a density to put, and the density for radiation is T to the fourth. That's Stefan Boltzmann. It's not, in Robertson Walker Friedman, of course, what you do, you use the ideal radiated fluid plus the Einstein equations to both go. Okay, we could do that here, but maybe it's not the right moment to do it. But I can't help it now to remind you. And R, and how does universe expand? Expands adiabatically. That's the first assumption of ideal fluid that expands adiabatically. We expect that there are no crazy, violent things in the expansion. That's Big Bang. That's the idea, central idea. What it means, so somebody didn't capture this, it seems to me, the way you look at it. This is equivalent to saying that R cubed times T cubed is also a constant. Now R cube is a volume, and T cube is a density. Remember the density of particles at high temperature is given by T cube. When you are at very high temperatures, and I am at high temperatures, I went to the early universe, so temperature is bigger than the masses of the particles, I want to really see what happened in the early universe, then the density goes as T cube, right? If particles are very massive, then you will have exponential suppression of Boltzmann. But when there are no masses dimension, you know, n has a dimension of I see you not okay, it's completely clear, or yes. So what I meant, but somehow you were not telling me, yeah, but it's obvious. We believe that the number of species is preserved. Universe is defined as universal, therefore I don't want you to speak of parallel universes to me, because then you please be sure what you mean by that. Universe by me is everything there is. And I believe, as you do, that nothing is lost. Of course, there could be, there are first order phase transition by the wave and entropy. This is a conservation of entropy, as you watch. Entropy you measure as the number of states. Okay, and then you say this is conserved. The universe expanding, this is what is happening. It's expanding at the cost of that cooling down. But nothing is lost. It cools, gets bigger. Cools more, gets even more bigger. Okay? So this is a very simple assumption. Now it turns out that this number is large. How large? Well, it's from here. Today this is equal, so I can compute immediately if I know the temperature today. So what is the temperature today? About 10 to the minus 4 electron volt. So I can compute R times T, and R times T is about 10 to the 30, which is 10 to the 28, the same 10 to the 30. It's amusing. I was once in a seminar of Dirac, 74. I wanted to say, I almost automatically said that Dirac was somehow old. I really bugged me because of my age. He was not in good shape. He was sort of trembling and he looked like an old man. And he was saying that there is a problem in this, and we thought that Dirac sort of gone crazy a bit. You know, there was a great physicist. We had completely moved. There were a bunch of us going home after the seminar, walking. Rockefeller University was a different place. He said that there is a disturbing thing for the evolution of the universe. He's anticipated the problem of inflation. He was actually speaking, he wasn't so clear about the horizon problem. The problem is here. RT is 10 to the 30. So R is 10 to the 30 over temperature. We just said that dH is m Planck over T squared. So that means that R over dH is what? Help me? Is 10 to the 30? T over M prime. This is 1 today. This is how I define the things. This is 1 today. Put the numbers, you get the number of order 1. I may have moved by an order of magnitude or so. And notice when the temperature increases, this number starts increasing. So even when you go to nucleosynthesis, which is MeV, which is orders of magnitude bigger today, all of a sudden the universe consisted of extraordinary millions, billions of casually disconnected pieces, okay? That's it for isoprop. So it's hard to imagine. You see, the universe didn't communicate to each other. It's hard to imagine that you would have just domains of plus V, that you would have vacuum everywhere the same. You would say, well, where it's casually connected, it's V, but then maybe there is another peak which is minus V. What will happen between V and minus V? What will happen if really the universe had this thing? Okay, this is what I want to talk about. I gave a little reminder of cosmology to motivate it. Really, I can talk about it without, but the issue becomes interesting in general. Okay, it rings the bell now. So, what would you expect happens? Notice I cannot go continuously from V to minus V. It's a discrete thing. So I would imagine that will cost me energy. There must be some non-trivial energy, okay? In other words, there must be some wall that carries a lot of energy, okay? And I'll show you that there is a wall between V and minus V.
There's always the example of magnetism about this spontaneous symmetry breaking and domain walls, such that in high temperatures we have random motion, but as we cool down, we go to the vacuum. So if we have two different vacuums, I don't know how it could be in this example, we have two different regions that align differently. So the boundary is called domain law, right? So in this case, we have different vacua that we can.
The question is what I will get. We'll go to a more complicated situation after I do this. This is a discrete symmetry. It's not so interesting. You're going to ask me what happens when I have more complicated symmetry. Yeah, sure. That's the first question we will ask.
I can understand the physical meaning of being two different vacua at two different places. Like, does it feel different? I don't see anything different.
Oh, they would, well, the question is what will happen when they meet. If you could really cross the domain wall, imagine that this discrete symmetry CP violation. Imagine that I broke CP spontaneously. Now, that means that a particle in one domain is an antiparticle in the other world. But in other words, what distinguishes this sign of V and minus V would be the phase that designs the particles. So, for example, it wouldn't be cool for these guys to meet and shake hands if they somehow pass through this wall. Now, of course, what may happen when you pass through the wall that you actually change and become, that's now an interesting question. Bottom line is, if there was a way to communicate, they would know.
So two different patches of space can have different physics.
They will have different physics, right?
Okay.
Well, of course, they would call particles particles and antiparticles antiparticles. They somehow have to meet in that original form, and then we'll talk about it, whether they can do that.
We cannot tell which vacuum we are.
We cannot tell which vacuum is. So it's most likely if I manage to press the wall, I will become that other species, okay? So it may be meaningless. This will be an important question. You're asking a fundamental question that confuses people, and we'll turn to it in 10-15 minutes. Because we realize that I just outlined this, and we don't stop without. If we need 5 minutes more, should we do that? Just we have to outline this domain wall. This will be simpler, and then we'll come back to the physics of that. Let's show that there is a domain wall. A domain wall will look like this table. Above it is plus V. I'm going to pretend I'm interested in a very large domain wall. I'll take it infinitely large. So for simplicity, let me imagine that I have a X and Y surface which will be domain wall. In other words, I have a one-dimensional system. I'm just varying the coordinate Z varies. So if I find something, it will be infinitely large. Okay?
Infinitely large in which, so like what?
I'm suspecting that there is a wall between these two vacuums.
Okay.
I will look only at the infinitely large wall. This wall could be small, it could have some size.
Okay.
And I can tell you what I mean by small compared to the size of the universe. Well, most likely it has some finite size. I will just now pretend that it's infinite. If I do find, I'm looking for solution so that in the xy plane, infinitely large. And I'm trying to find a solution that if I go in this direction, I will come to the vacuum V. If I go down, I will come to the vacuum minus V. I'll be more precise. I'm looking now at a static solution. So I'm looking at a static solution of this Lagrangian, of these equations of motion, or Lagrange equations of motion with finite energy. But when I say finite energy, I will actually look at the finite energy per area, because I'm interested in a large domain wall. So large that actually basically the energy is infinite, but I won't worry about that. Okay? I hope that's clear. But it may not be clear yet, it should become clear. So what it means, first, the notice that this energy over S will be 1/2. There is only one variable now, Z. I have a one-dimensional problem. If you wish, forget it. You just think that I'm thinking of a one-dimensional problem. I have one space and one time. But physically, what I mean, it's a big table.
So in the Lagrangian kinetic term, we have a spatial derivative term.
Yeah, of course. I will write the Lagrangian in a second.
This is that part.
This is coming from the Lagrangian. You know, the energy. Lagrangian, of course, goes with the minus sign. This will be with the plus sign.
Like it's the energy that's stored in the configuration of field in the space.
We'll see what it is. I'm just writing my Hamiltonian. You agree that this is my Hamiltonian? In the situation where the field depends only on Z. There is nothing else, right? There is no, I don't have to worry about the time derivative, okay, that you know, the changes. I will just get this static situation. Phi is constant. So let me call it, I'm looking at some solution of this equation, phi wall. You agree, if I want this to be finite, either think of it as a one-dimensional situation or just think of it per unit area, okay? We are not worried that area is very large. If I want to be finite, that means that this goes to 0 at infinity, goes to 0 at infinity. My usual argument. Integral has to vanish for, this is over dz. And I'm integrating from minus infinity to plus infinity. It's very good. Infinity is only 2 points. Okay, in this case, the infinity manifold is very simple. Why not I write it here? M infinity is plus infinity and minus infinity in Z. And remember there was M0, which was also 2 points. You know, I have the same manifold. I can imagine that there could be a map in principle. We can map manifolds on manifold. You heard of these topological maps that we call homotopic maps. You can map a circle on a circle. You never heard of that. But you can do that. You can say, when you're moving on your circle, I have some circle. You go once. If I'm fast, I'll go twice. If I'm very fast, you know, turtle and Achilles and so on. We know that Achilles is actually faster than turtle, right? You know. This will be useful for us. So I'm learning immediately. When I'm at infinity, this goes to the vacuum manifold. In other words, at infinity, I'm just learning that phi goes to plus or minus v at infinity. Whatever solution I find, if such a solution exists, okay, we'll have to go to the thing. For example, vacuum is one such solution. Take phi equal V everywhere. That's a perfect solution. The energy is zero. The energy stored, it's constant. The energy stored here is zero. The energy stored here is zero. Look how I wrote my potential. You agree? So one solution, let's call it phi vacuum, which I used to call phi zero, which is say plus V, is a solution with E over S, zero. That's my vacuum. That's why I call it vacuum. Okay, and we live there. I mean,
But yet we're trying to go from one vacuum to the other in a finite, with a finite amount of energy, right? I mean,
that's what I'm trying to achieve. I'm trying to say this is a trivial solution. There is also an even trivial solution which I will call phi wall. It's such phi wall goes to plus V when Z goes to plus infinity, say, and minus V when Z goes to. Let me see if I can find such a solution. That's why I call it a wall. I want this to connect between my vacuum. Interpolate. This will carry some energy because it's not vacuum.
Because there is a derivative, we need to change.
There is a derivative, there is a potential also. There will be a potential energy. Notice if this goes to V, it goes to minus V. When Z goes to zero, I will have to pass through zero. This is a continuous function. Let's plot it. This is phi as a function of Z. When Z goes to infinity, I'm here. The only way symmetrically to connect is like this. This is V, this is minus V. Interesting question is how thin is this, how thick it is. It will have sense to talk about if this is very thin. What does it mean thin? That I'll get some kind of exponential thing. Then I will be happy I found some interesting solution with a finite energy, right? Imagine that I do that. You know, you can just picture it like this. Try to imagine it just like a jump. Imagine it's so thin that it's V, and then it jumps very quickly over very thin thing and becomes minus V. I'll do this kind of energy consideration, but I want to do the exact equations which will be very easy to write. Why is it easy to write? You will be surprised how easy this particular situation is, how nicely it takes us to the monopole, because from here, from the Lagrangian, I have my equation. This is Euler-Lagrange equations of motion. That means that d square phi over dz squared, let's slide this now, whole, minus I is V equal dv over d phi. Okay? From here, do you agree that this is equivalent? Let me see if you see. I'm taking a derivative with respect to z. What is this on the left hand side? That's the second derivative times d phi over dz. If I multiply this, so I have a multiply on the left and right with d phi over dz. And I get immediately this equation. You can bear another 5 minutes, maybe 10. It's going to be like this equation. I've just proven that 1/2 d phi over dz squared is actually equal to V plus a constant for my solution. Okay? The derivative. But notice that the constant is 0. How do I know that the constant is 0? Because when I go to infinity, both have to vanish. Here was the argument. I'm asking for a finite energy solution. This is very important. The same way that I fix here, I must apply in my solution. I want the energy to be finite. It doesn't make sense to talk about solutions that don't carry finite energy. You see that this is going to be well defined. The way electron is well defined. Electron, the only difference between this domain wall and the electron, that this guy will carry some size, obviously. What will be the size for us? That will be the configuration when you are not in the minimum. We call that size. Well, you'll understand it in a second. So I can drop the constant. Remember V of phi. Let me keep it there. Notice that the equation now becomes very simple. d phi over dz, all is all, it's equal plus or minus v squared. I've just taken the square root of that equation. 2v. Do you agree? You know this? Can you recognize this? When it's a minus sign, when it's a plus sign, you will have cosine or sine. Tangent, when it's minus sign, you get hyperbolic. See immediately, please, that phi v is v plus or minus. Well, phi wall is, let me call it, we call this anti-wall, minus v. Why do I call a wall when I'm going from minus v to v? I call the minus wall when I'm going to v from minus v. Okay, just let's focus on this one. You see, here you get 1 over cosine square, and here you also get 1 over cosine square. Just take the derivative. Derivative of tangent hyperbolic is 1 over cosine hyperbolic square, but this minus this v, that's why v has to be outside. You see now it's exponentially thin. So actually the delta wall is 1 over v. As soon as you are going to a distance bigger than 1 over v, you are ended up in a vacuum. I know what delta is. It's 1 over v. What else could have been? That's the only scale in the theory. I took lambda equal 1. On the measurement grounds, well, it could have been 2 over v. I normalized to be 1 over v. Now you can see what I did. Potential. I didn't put a factor of 4 or something. Okay. And I think I got it right. I was checking this last night. We found this famous wall solution. And we can also compute its energy. How would you compute the energy? Notice that E over S. What is E over S? Notice that this is just 2V. But then use this equation, and you will see that this is equal to the square root of 2V times d phi. Because dz is 1 over square root of v times d phi from here. From here. Sorry. Why not I write it? Why not I write this equation? The equation was d phi over dz is equal square root of 2v for wall. This is the equation I should keep. It's a useful equation. This is the equation I solved. It's here. Okay, notice. I should have written it, just so. And this is the equation for minus v to v, v squared minus phi squared d phi. So it's something over the v cube. Again, on dimensional ground, it had to be V cube. It couldn't have been anything else. I think you get 4/3. It should be trivial to check it, but I'll get 2 minus 2/3, 6 minus 2. It seems to be true. It's trivial, right? I don't care about the coefficient, but I know how much energy the ball carries. It's V cubed. Because of the dimensions, E over S. E over S, you will see, is V cubed. Energy is V cubed times surface. And that will give you dimensions of mass. One last comment, I should finish. Just the but at the moment, it's good to understand this. Physically, you see what it's doing is this thing. What is really happening? Let's try to see here. I think it's useful. This is so thin that you can imagine that this guy is coming here, and then in some almost small space jumping from V to V. If I do like that, what will I get? In this picture, a very thin wall. Outside, I'm in the vacuum, energy 0. Inside, here this is 1/2. The change of phi is from V to minus V, it's 2V, over the length 2 delta. So this is V over delta squared. Plus, and V of 5 is 1/2 V to the 4th times 2 delta. Well, this times 2 delta. This is the energy change in energy carried by asking field to jump from one value to another. That costs energy. At the same time, we are asking it to be away from the minimum. So this is the contribution here. Or times. No, this is okay. I put delta outside. It's okay. Let's to understand that there is a half and half. Let's cancel a half. So let's write this V2. This is V square over delta plus V fourth delta. Okay, I invite you to be awake for a few minutes. Notice what is happening. This term, because you are away from the minimum, you are in the maximum of the Higgs field. This wants delta to be 0. Here you have to jump over some distance delta. You prefer delta to be infinite. It costs you less energy. This wants delta to be infinite. This wants to be finite. What's going to happen? They will match, and it's easy to compute that. Notice that d E over S over d delta is minus V square over delta squared plus V to the 4th, and this should be 0. I have a stable situation when these two guys match each other. When I minimize it. Notice that I get that delta is 1 over V. This exponential thing is so thin that it's naive pretending that the jump is instantaneous actually gives a good same reasoning as here. Because this is really what exponential things do. Domain wall costs us energy because I cannot go continuously. If I had a U1 transformation, we'll have to talk about it when we come there. Then of course I can go from one vacuum to another continuously. That doesn't cost me energy. But when I have a discrete situation, I'm either here or here. In order to cross this, costs me an energy. And I know how much energy, and I know what is the thickness of the wall. So what we have to do, we have to try to think what this implies for physics, for example, for cosmology, if such domain walls exist, and then to generalize it to cases of more interest, like standard model when we have gauge symmetry.
So when we give the example mentioned mapping from one circle to the other, is it the same thing where we try to match here two infinities to two vectors.
Right.
So
You always map all the solutions, all these objects, it's like instances we talked about, were mapped from points at infinity into the points of your field values. And it turns out, and it's always asking for something to be finite. There we wanted energy to be finite, remember? So we had to be in a pure gauge. So there we could define the values of the gauge field and the infinity. Again, I want the solution, apparently very different from that one, but then the logic is the same. I want the energy of my wall to be finite. That required me that when I'm in infinity, which I raised, I am in the vacuum of the Higgs fields. Whenever the infinity has the same topology as the vacuum, you will be able to talk about the map. And the solution will be those maps. What I have to show you, a number of things, that I could have solutions with bigger numbers and so on, but what I have to show you that this domain was stable. You have to ask me, how do I know that they really exist? Why doesn't domain will decay into vacuum? 2 vacuum, 5 vacuum, I don't know. That's what I mean by that even.
Didn't we show that by derivating to the thickness? This is a stable solution. That doesn't
In a sense, you're right, in a sense. Well,
or if you have an odd number of domain walls, we cannot wind it out. How can I say?
right, good. There is a winding here, so you suspect this to be stable because this, how can this can never transform into the vacuum because the vacuum stayed here. I've had it, but I want to show you that whenever you have a situation like that, I can show you that there is a conserved charge. I find the charge because it's conserved. This domain wall will carry charge. I could do it today, but I think it's too late. It's not good. It will be too much. So I'll take tomorrow 10 minutes, 15 minutes to finish this. And then we go to the monopoly. So tomorrow we have one lecture, so that it's not too much, or it's Thursday, or you want to see tomorrow. We can play by ear. We can decide at the last moment.
We could have different, like, vacuums and jump from one to the other.
Can I have more vacuum?
Yeah.
Yeah, good question. Yes, in principle, why not?
Maybe we can change the potential. And have
Change the potential to have, if I have a higher power, I could have even more vacuum and I could have even more interesting situations in which I could charge. Yes?
For example, I remember I have seen something of this somewhere, and we can play with maybe a sine or a cosine in the potential, so we will have different.
Right, you may have a called theta vacuum. Fine-Gordon, so-called case has that. I've chosen the simplest. Whenever I start something, remember the rule that I had always, we start with the simplest. And then depending on how far we go. This is why it's good to do this solution, because you can study this from the energy point of view, from the vacuum point of view, from the constructing the solution. You have an explicit form and so on. We will find the conserved charge. You can really sort of nail it, you know.
Is it called topological charge?
This is called a topological charge, precisely. Because there is nothing like, I mean, you see, there is no conserved current associated with it. This is discrete symmetry. I don't have a continuous symmetry. So that means that it's some very charge. It means that the charge is automatically satisfied, and not by using the equations of motion. That's why we call it topological charge. Nothing to do with Eminator theorem. Shows you that by using equations of motion, right? When you have a symmetry, you use equations of motion, and they give you the equations of motion means the invariance of the action, and they give you the conserved charge. That's the same thing. Here I can't do that, okay? So I can't expect this to have its sort of current will be trivial. I'll write it down so that it's good to have it. Look at this current. I have a two-dimensional system. Remember, I froze x and y coordinates. Okay, you know I have only time and z. simplified, okay? You can view it any which way you want. The x and y coordinates are free. Notice that d mu, j mu is 0. Trivially. Not because of equations of motion, okay, that's what is called topological charge. But enough said. Tomorrow I will look at this details. Okay, you guessed it. Or heard it. This is a fascinating experiment. This is extraordinary, especially when you come to monopoles. The next solution would be, but I think there is not enough time. If I go gradually, as I do in my notes, then I will do the string. I'll go from domain wall, which is the simplest. Remember how I taught spontaneous symmetry breaking? I had a discrete symmetry, then I had U1. In the case of U1, you can imagine that U1 has cylindrical symmetry. You can get a solution which is infinitely long string. The third example I gave was SO3, breaking down to U1. SO3 has a spherical symmetry. The manifold is S2. It's broken down to U1. It's not surprising that this spherically symmetric solution I will get. Okay, here is a planar solution with a symmetry. My domain wall is just this table. It's very big, so if it's very big, I have a symmetry z going to minus z. In the case of a string, I have a symmetry of a circle. And in the case of that, that's why it's going to become a monopole. It's not surprising. I have a compact U1 when I break SO3, because Q is T3. Okay, I'm anticipating the miracle, apparent miracle. Okay, this is how Hoff must have figured it out. Because how in the world would you go and look for a solution? Understood that such a miracle should happen.
So you told that if you have charge quantization, this would somehow imply monopoles. So we will see that here the topological charge so-called will be quantized by integer numbers, which are the binding numbers. And this will imply through those examples that we can charged, quantized charged monopoles.
Okay, what we did, it doesn't matter. SO3 theory has charge quantized. And then you suspect, if monopole brings charge quantization, then it's kind of natural to think that maybe charge quantization brings in the monopole. In the SO3 theory, charge is quantized. And I'll find, you see, what is the solution, by the way? It's just a wall full of Higgs field. By the way, you will see this in my notes. It's wonderful, okay? If you decide that you want to learn about this more, it's fantastic to look at the gravitational energy of a domain wall. Because the energy momentum tensor is very strange. You and I are used to simple energy momentum tensors. For example, we are used to matter when density is something and pressure is 0. Of course, when you're in the early universe, remember pressure of radiation is that's why early universe is so strange. It's expanding because it carries pressure, and pressure is the third of the density. And domain wall has some crazy energy momentum tensor. So when you calculate the gravitational pull of a domain wall, it's anti-gravitational. Such a large domain wall, if it was static, now it's hard to imagine it's static, so maybe this, I'm thinking a static thing. If you produce it at some very early violent universe, I think probably would carry a lot of energy, so this was naive. There should be then change. But anyway, you and I would feel it anti-gravitational, it would be amazing, right? The thing it has a positive energy density. Because what determines gravity, it's not just density, according to Einstein. It's T mu nu. It's the trace T mu nu you will see when you look at the slow-moving bodies. So this is a very nice example of how gravity can change when you have relativistic field theory system. It's a very strange thing, the domain wall. It's full of Higgs field. It's built of Higgs field. It's full of Higgs field inside. A monopole will be like that. It will be full of Higgs field inside. And outside will produce something that looks like a field with magnetic charge. It's good that you had interest in that. In a sense, it sort of brings us back to the system of the study there. It gives a deeper meaning and completes the symmetry breaking. You see, now the beauty of symmetry breaking is that it can lead to interesting geometry, topology, homotopy, and not just perturbation theory. Okay. I stayed up very late. I couldn't. We went for dinner, and during the dinner, I find this subject really fascinating. What we should ask the question, by the way, just that we are now, let's just chat. We could ask the question: how, if these things exist, what will you do to cosmology? Imagine that there is a big domain wall that separates two vacua. It would change the picture of Big Bang. We should put the numbers. Now the thing that we have to decide, we said we could even meet on Saturday. Are we going to do that? Are we in the mood to do that? What do you guys think? This is it. Whatever you wanted to learn and you were afraid to ask, or not afraid to ask, from me, it's this week or never. My wave function will sort of, it was spreading recently. We are normally very classical, you know that, right? I don't know last time when you put the numbers on classic, how would you call it?